15 seconds. Guidance internal. 13, 12, 11, 10, 9, 8. Ignition sequence start. Engines armed. 5, 4, 3, 2, 1. All engines running. Launch commit. Liftoff. We have liftoff at 9:34 a.m. Eastern Daylight Time. The tower is clear.
NASA, the National Aeronautics and Space Administration, presents Aeronautics and Space Report. This is the story of the upcoming flight of Apollo 15, as told by the men who will fly the 12-day mission.
The primary mission objective of Apollo 15 is to land at a site on the moon called the Hadley Rille and collect documented samples from various geological features within the area of the landing site. We might also add that a primary objective is to remain in lunar orbit for 6 days with the command and service modules, gathering scientific data around the moon with the scientific instrument module in the command and service module.
40-year-old Dave Scott, the man in charge on Apollo 15. This will be Scott's third space flight. He flew previously on Gemini 8 and Apollo 9.
Well, of course, I'm probably the oldest rookie in the program, but looking forward very eagerly to this trip, because I think it's going to be certainly one of the greatest missions to date, and certainly one of the most complicated.
Sharing the workload on the moon's surface, lunar module pilot Jim Irwin, 41.
The experiments that we're carrying are basically geochemical experiments, and with these experiments we hope to be able to map the surface of the moon, correlating that with the rocks that we get from the surface of Hadley Rille and with some of the rocks that we've had on previous flights.
Orbiting the moon while Scott and Irwin are on the surface, 39-year-old Al Worden, command module pilot. Approximately 3 hours after launch from the Kennedy Space Center, the crew of Apollo 15 will head out 240,000 miles toward this spot, the Hadley Rille, located in the foothills of the moon's Apennine Mountains.
The landing site for Apollo 15 at the Hadley Rille is a very dramatic site. We feel that it will be quite spectacular when you get to see it on television while we're there. It's essentially on a flat plain surrounded by mountains on one side and a rill, or a meandering gorge, we might call it, on the Earth on the other side. The mountains to our east and north and south range anywhere from 11,000 to 15,000 feet high, and the rill, or the gorge in front of us, is like a canyon, and it's about 1.3 kilometers across and 1,000 feet deep. So it has some very significant terrain features, and something I'm sure that everybody will be impressed with, at least from the standpoint of visual observation when we get back.
Astronauts Scott and Irwin will travel farther and gather more samples for scientific study than any moon landing team so far. They will be able to do this because of the Lunar Rover, a four-wheel battery-operated vehicle.
Well, the rover weighs about 500 Earth pounds, which is slightly more than 80 pounds on the moon. So you can see it's a rather light vehicle on the moon. As a matter of fact, if we had to change a tire, one of us could hold it up. Although with the wire wheels, it won't be necessary. The Rover is folded. Its wheels fold in flat to the body, and the body folds up in two pieces. And it's stowed in Bay 1 on the left side of the front of the limb.
Now, as far as the drive on the Rover itself, the control for it is all built into this one stick right here. It has the brake. The brake is the rearward position of this stick. Brake's released now. To go forward, you merely push the stick or the throttle control forward, and it maintains that position, should maintain that speed depending on the terrain. To go backwards, you release the reverse inhibit and just rotate the stick aft. And then to turn, you just move the stick to the left or right like a roll input in an aircraft. And that will turn the wheels and you'll move in that direction. The instrumentation for the vehicle is all presented on this one panel in terms of amp hours, voltages, then temperatures on the batteries and on the drive motors. We also have a display here for our navigation system, which is will be most helpful on our extended traverses from the LEM, because on EVA-2 we'll be moving away as much as almost 8 kilometers from the lunar module.
Traveling at speeds of 5 miles per hour or more, Scott and Irwin will be able to explore roughly 25 miles of the lunar surface as a result of their added mobility. There'll be television, too.
The television has been developed to be carried on the rover and controlled remotely from the ground. So every time we make a science stop, we enable the television within the communication systems on the rover, and the ground will be able to point the TV in any direction within 360 degrees, elevate it and depress it, and also zoom it. So you'll perhaps have a better view of many things than we will, because you'll be able to watch both of us at the same time.
During their 67-hour stay on the moon, Scott and Irwin will move out of the lunar module and onto the moon's surface for 3 major work periods of extravehicular activity called EVA. It is during this time that they will explore and set up scientific experiments.
On EVA-1, for instance, we'll be going down to the front first, doing our geology investigation down there along the Apennine front, and then over to the Rille. And then coming back to the LEM, we'll be unstowing the ALSJ packages and then deploying the ALSJ about 300 to 500 feet west of the LEM. I'll be doing the bulk of the deployment while Dave is doing the drilling operation.
Well, the lunar drill is part of what we call a heat flow experiment. First, we were able to drill a hole deep into the lunar surface and implant temperature sensors, which enable us to measure the profile of heating, if you will, from depth below the surface to the surface. This will give scientists a signature of what the surface consists of and how its heat flux changes. They can extrapolate this into possibly an explanation of the origin and the history of the interior of the moon. The second aspect of the drill is a core, or a deep penetration of the surface and gathering of material some 9 feet below the surface in an extended core which is brought out intact, showing the profile of the surface to depth.
Al Worden, the command module pilot, is responsible for the major science experiments conducted while in lunar orbit and on the return trip to Earth. As they travel toward the moon, a panel door on the side of the service module will be jettisoned, exposing the cameras and scientific instruments, 10 in all. These include a gamma-ray spectrometer to measure the chemical composition of the moon's surface, a panoramic camera, a mapping camera, and the sub-satellite, a satellite to be placed in orbit around the moon shortly before the crew heads earthward. The sub-satellite should stay in lunar orbit for a year.
The sub-satellite is what I would term a passive experiment. And when I say passive, I mean in the sense that it's not powered in flight. We eject the subsatellite from the command and service module. It goes into an orbit which is then only perturbed by the gravitational attraction of the moon. The subsatellite is a particles and fields satellite. The main effort in this particular satellite is to measure the particles field around the moon, such as the plasma flow, solar rays, magnetic field, magnetic particles, and this type of thing around the moon. Because of the way the satellite is built, and because of the way the data is transmitted back to Earth, we get a very nice byproduct from the satellite, and that is that we can track the subsatellite with radar, with radio signals from the Earth, and we can position it precisely in its orbit about the moon, and we can watch the perturbations of the orbit of the subsatellite, eventually arriving at a very good model of the gravitational field of the moon. And there's been a lot of talk about heavy spots on the moon, the so-called mascons. Because the subsatellite is completely unpowered, it's completely at the mercy of this gravitational field, and any heavy mascon that it sees perturbs its orbit. And we can calculate this. We can measure it and then calculate that gravitational field.
It is Worden who will go outside the spacecraft at about 16 hours after leaving lunar orbit on the way to Earth. The purpose is to retrieve film from the 2 cameras located in the Scientific Instrument Bay. At the Manned Spacecraft Center, Houston, Worden practiced this maneuver underwater. We asked him to describe his planned trip outside the spacecraft.
Once the hatch is opened, we'll take the TV camera and the 16mm data acquisition camera, mount that on the hatch, the command module hatch, with both cameras pointed toward the service module where I'll be working. Once that's accomplished, then I'll go very slowly down the handrails to the service module, staying away from the reaction control system engines or quads, which are just off the side of the path of the EVA. Go down to the service module, get situated in the EVA restraint boots, which are located on one side of the service module. And once in that position, then I'll remove the thermal and contamination covers from the pan camera cassette first. Once they're removed, I'll pull the cassette out of its bay, tether it to the left wrist, and then very slowly come back the handrails, back to the command module, stow the cassette inside the command module, where Dave Scott will keep track of it and hold it until the end of the EVA. Then I'll go back down the handrails and essentially repeat that process with the mapping camera cassette, tethering it to my left wrist and bringing it back into the command module.
Scott, Irwin, Worden. If all goes on schedule, they'll lift off from the Kennedy Space Center, Florida, in late July. Here, they summarize their feelings about space and this mission.
Well, I think it's always important for man to have a new challenge, maybe a physical challenge, but certainly a challenge to his imagination. And I think that the fact that we're going to the moon is just another step forward. I think we have to go to the moon. We have to explore it and really learn how to explore another planet.
The space program is one of those things that this country has, which is really could be and probably is for a great number of people in the country a driving force. It's expanded technology immeasurably. Computer industry, hardware industry, equipment, anything you want to mention, even management, has benefited tremendously from the space program. And I think that we really need to keep this kind of technology going if we're going to be leaders in the world.
We feel if we can learn the history of the moon, we can extrapolate it to the history of the Earth, and perhaps with this knowledge discover the manner in which our resources were created and the manner in which we can discover new resources and preserve what we have. The overall result being a continuation of what we have on the Earth and enabling us to better understand our own planet and the manner in which we have to preserve it in order to sustain man.
This special Aeronautics and Space Report brought to you by NASA. This is where the suits worn by Apollo astronauts are sewn, cemented, assembled, and tested. ALSJ Industries in Dover, Delaware is where they put it all together. Arms, legs, torso, boots. The end product? An incredibly reliable, custom-tailored, hand-assembled life support system, a spacesuit. The initial measurements taken at NASA's Manned Spacecraft Center in Houston are the first step.
When an astronaut is assigned to a particular flight, many measurements are taken of his body, approximately 60. It takes 3 months from the time we have his measurements till we do have a spacesuit built for him. And there's a formula involved to give the man maximum mobility in a confinement of, you might say, a pressurized balloon.
It is in this production room that the balloon-like inner suit, called the bladder, is assembled. Individual parts move on a schedule that brings all the pieces together into an integrated spacesuit. Meanwhile, on the second floor of the plant, the white outer suit, consisting of 17 layers, is cut out and assembled. These include a layer of woven Teflon to provide resistance to abrasions, a layer of fire-retardant fiberglass called beta cloth, and a series of nylon restraints to hold in the inner suit like the skin of a football. So close are the tolerances that if a part is cut out and doesn't match the pattern by a 32nd of an inch, it must be recut. Gloves must fit so perfectly that they are made from plaster casts of the astronaut's hands. It takes 160 hours to make a single pair of molds and gloves. During qualification testing, suits are subjected to 10 times the design requirements of a lunar mission. Another critical area are the pressure tests. To be accepted, a spacesuit must have practically zero leakage when pressurized. Each of the prime crewmen on an Apollo mission has 3 suits made: a training suit used till the day of launch, a flight suit, and one that serves as a backup. The last stop is called the fit check. Here, astronaut Charles M. Duke, lunar module pilot for the upcoming Apollo 16 moon landing next March, tries on one of his suits for size and comfort.
Okay, sir, you're at vent pressure. You want to stay there?
Yeah, let me work it out a little bit.
The fit check is done in 2 parts. First, the inner suit is worn.
It does look like it's up higher.
Adjustments are made, and later in the day, the astronaut dons the 2 pieces, now put together as one totally integrated suit. It is here that the suit is finally accepted or sent back for additional changes. We asked astronaut Duke to comment on his suits.
Yeah, it's a good fit. Both my suits have been excellent fits. We haven't had any trouble at all. This is my second time up, actually the third time up. I have a training suit and 2 flight suits, 1 spare and 1 prime suit. Both flight suits just fit exceptionally well. Real pleased.
Like a jigsaw puzzle, the pieces forming a garment that the astronauts can wear with comfort and confidence are brought together. A garment that serves as a small-scale Earth environment in the hostile, airless environment of space.
Well, I think Apollo 15 is different in two major respects from previous lunar landing missions. The first and probably most significant is the fact that we have the capability to stay on the lunar surface for 3 days. Additionally, we have with us a lunar roving vehicle, which enables us to travel about the moon by wheel and cover a great deal more area than we've been able to in the past. We can cover a distance of about 36 kilometers and range as far as 7 kilometers from the landing site. Secondly, we have aboard the service module in orbit a scientific instrument module, which is a large bay full of scientific gear, sensors, and the like, which can essentially determine the composition of the lunar surface while flying over the surface. And by analyzing the return samples and comparing them with the service module data, we can essentially evaluate approximately 20% of the moon during the flight. And I think with this data, we should be able to significantly enhance the scientific knowledge of the moon.
One more? Yeah. Put it along your kitten.
What's the cat's name?
What? Christmas cat.
You're a veteran of space flights. Do you plan to do anything different during this flight that you didn't do during the other flight?
No, not really. It's just pretty hard to leave home because you want to stay close to the news and what's going on. And I think probably the thing that will make it the most different for me this time will be the fact that it is a summer flight rather than when the children are in school. And possibly, you know, this will make me get out of the house more, taking them and doing activities with them.
Following the tragic Russian accident, do you feel a little relieved now that the Manned Spacecraft Center is going to require your husband to wear his spacesuit on re-entry?
I don't really feel that the Russian tragedy has that much of a connection with our program. Naturally, I was upset. I've had the opportunity to meet 7 of the cosmonauts, and I feel that other than a language barrier, they have the same desires and the same drives and motivations that my husband and the rest of the astronauts do, and therefore I think there's a bond. And when something happens in their program, I know the first time there was an accident, I was surprised at how personally upset I was. But I really do feel very close to them, but they use a different environmental system. You know, they use the mixture of oxygen and nitrogen, and therefore I don't really feel we have the same problems that they do.
When you're away from the house, what questions are asked you that seem to bug you the most about the flight?
That question is, how do you feel? Because there really is no way you can put how you feel into words.
This is Kennedy Launch Control, T-minus 2 hours, 16 minutes and counting. All aspects of the countdown still go, aiming toward our planned T0 at 9:34 a.m. Eastern Daylight Time. Scientist astronaut Carl Henneis, who in actuality has been the 4th astronaut inside the cabin, giving the 3 prime crew members a hand as they go through their initial preparations and initial checks, now has departed from the spacecraft after completing his job. The astronauts, fully suited, are of course now on the suit circuit. Henneis has aided them in making some checks of the circuit to assure that they are getting a good flow of pure oxygen into their spacesuits. We also have made medical readouts on the astronauts to assure that we are getting satisfactory medical data. And at this point, a Houston flight is sending some real-time commands to the spacecraft to assure that we have the proper links between the control center in Houston and the spacecraft here at the Kennedy Space Center. All is still going well. The crew here in Firing Room 1 monitoring the status of more than 1 million gallons of propellants that now are on board the Saturn V space vehicle, and the mission is go. 2 hours, 14 minutes, 40 seconds, and counting. This is Kennedy Launch Control.
describing, if you would describe your approach to the landing site as you pitch over and you get your first view of your basin with Hadley on one side and the rest of the topography.
You've got it.
you tell me.
Well, I guess the first thing we're looking for, you mean describe it in terms of what we see, or
what you expect to see, first of all?
The rill, of course, we hope, is right in front of us, and we use that as a general guideline to the landing area. And from the rill, we look back up towards the east to a crater called Index Crater, which is the crater on which Al Worden will do his landmark tracking in order to tie the landing site into the command module orbit. And it's a very prominent crater with some distinguishing features. And once we find Index and we move slightly north and slightly west to the landing site, which is among some other craters which are identifiable, and then check the computer, the LPD landing point redesignator, to make sure it's taking us to the right place, and try and get an assessment of the general terrain and the debris on the kind of rocks or boulders or craters or what we have. And from there on down to on the order of 400 feet or so in the automatic system, and then we intend to take over manually at about that point and go ahead and land.
Will you see the Apennines at all?
Yes, it's off to the left, but probably I won't be looking at them too much. My main concentration is on the rill and the landing site, and of course just to the south of the site is the secondary cluster, the crater cluster down there, and that's also very prominent. That's in the field of view in a window. And if you haven't had a chance to see I'm sure you haven't, the model at the Cape that we use in the simulator.
Yeah, I have.
Have you seen it?
I've seen it. Not from the limb, of course, but I've seen it.
But you've seen the model.
Right.
That's great.
It is.
It's really great.
Really,
yeah, you pitch over, and one of the advantages to this landing site is that you just can't miss with that rill there. I mean, you know where you are right now.
After you land and open your hatch, your little stand-up EVA, that'll be your first really good look at the whole terrain. What do you expect to see? What do you...
To look for geological formations and significant items which are on the mountains to the north and the east, which we'll probably not have a chance to assess later on, and to see if there are significant differences between those mountains and the one to the south on the Apennine front that we intend to visit. So we can say, gee, the ones to the north look like the ones to the south, therefore the ones to the south probably have the same material, or the ones to the north are completely different. And this gives us an idea of what perhaps the gross features are within the area of the landing. And we take the photography, we get a pan, and some 500 millimeter, hopefully, if we have enough time. And there's a lot to do.
People ask constantly, why is it necessary to go back to the moon? Why do you think it's necessary, if you do, and I'm sure you do, to proceed with the last two Apollo missions?
Go back to the moon?
On 16 and 17. How can we tell the man out in Iowa why it is necessary, after you're doing all this on Apollo 15, those two missions, the fate of those two missions hinges on success of yours?
I think they're fairly independent at this stage of the game. I think they can benefit from our mission by what is learned from our mission. On the other hand, if we didn't fly 15 at all, I think those missions stand on their own 2 feet as being necessary to accomplish their objectives.
If the rover had some malfunction, didn't work at all, you couldn't get the thing started, how would that affect your production of scientific data on the moon?
It significantly reduces our capabilities, obviously, because the rover is valuable for 2 reasons, one of which is to cover a great deal of area, and the other, of course, is to do it at the least expense to the crew, and that's metabolic consumption and our consumables. It's a lot easier riding than walking. And I think if we don't have the rover, we have walking traverses planned. We get to the rill and we get to the front, but we lose the north complex. And I wouldn't say that's 1/3 of the mission lost, because we will accomplish the major objectives, and the Hadley landing site was chosen for that purpose. And one of the reasons we're landing on the northern part of the Hadley Rille is because we can accomplish the major objectives without the rover. But it will significantly reduce our capability, no question about that. On the other hand, that's why we have the rover, because it significantly enhances our capability.
Getting from the moon to you, for a moment, what are your plans for the future? Do you plan to stay in the space program after you get back to Apollo 15?
Well, I think one thing we're obligated to do after this flight is spend a fair amount of time with the scientific community in debriefing what we've seen and what we've done. You know, we're now in a mode in which our interpretation of what we see has a great deal to do with the ultimate results of the flight, because we see and we gather samples for a reason, and we describe the front and the Rille with what we see, and we've been working with the geologists for a long time now so that we have a good communications going. And I think one thing we have to do is sit down after the flight and go over every photo and every sample to try and help them interpret what we've seen. And I think that's going to take a long time. And old Al is up there for 6 days, and that's a lot of looking. And I really think that we'll spend a lot of time debriefing the flight. And past that, I really haven't given it much thought. Because the closer we get to this flight, the more we see in it, you know. And from about 7 or 8 months ago, it almost seems like there's going to be more to do after the flight than there is before the flight.
Well, have you thought to whether you might like to fly again if the opportunity ever came? Or
oh, sure.
Rather, or maybe take a administrative job within the space program here?
I think whatever is appealing and a good challenge. I like the space program. I feel like I understand it. I feel like it's a significant thing. I think we need to continue with a strong and viable program, and I'd like to be able to contribute something to it.
Do you think you will be, that your age will be a factor, a detrimental factor when it comes to the space shuttle in 4 or 5 years? Is that going to be, you going to be too old then, or do you think they're going to be using guys 40 years old for space shuttles?
Hey, Al Shepard was very encouraging. You know, if you could take an old fellow like that and see what he did, that's very encouraging, isn't it?
And you look a little bit younger physically than he does, too.
Oh, I'm a lot younger than old Al.
Well, you'd like to stay around and try the space shuttle if it worked out then.
You guys will support us and
get the thing up.
Get the thing up there. I think that's it's a good challenge.
Well, you're from a military family, and am I right on that? I mean, you're going to go back on active duty someplace and getting a general officer's rank and going out.
Gee, I'm on active duty.
Well, I mean, back out on at an army post someplace, not a.
Well, I'd see a lot of similarities between MSC Houston and Army Post, I'll tell you. And differences. But it's an organized kind of thing. And, gee, I don't know, wherever the Air Force feels like I can do the most, it's sort of up to the Air Force, really. I work for NASA, but on Air Force loan. So I guess I will see what the Air Force has in store for me.
But we'll give you a star, make you commander or something. Would that be appealing to you? You'd say, no, I'd just sit here take an administrative job in NASA, and I like the program.
The Air Force doesn't often give you choices like that.
They don't say, Dave, come here, we got something we want to talk over with. They don't do that, huh?
Oh, no, they usually say, your next assignment is.
Dave, if someone gave you 3 or 4 or 5 days off between now and launch, and it's not going to happen, I'm sure, but what would you do? Get away from your flight, if that were possible.
You won't believe me if I tell you.
Try us.
You know what, if we had just 3 or 4 or 5 more days, what I'd like to do, I'd like to get in one more geology field trip before we go.
Is that right?
Yeah, we lost one day because we didn't get to do everything we wanted to do on one of the trips because of a lot of rain up in Duluth, Minnesota. But I wished we had time to go out one more time and get a good field exercise. We do go to Flagstaff next week for a 1-day exercise. But I'd like to go out and spend 2 or 3 more days, one more time before we go.
Back to Duluth?
No, not necessarily. Someplace that at the time we missed, that we went to, we did a lot up in Duluth. As a matter of fact, we looked at an orthosite to quite an extent, which is a rock we expect to maybe find on the front. and it's a crystalline, without getting into the geology, but if we find that one, why, it'll be a very significant find, I might say. It'll answer there are two camps. There are two opinions about what we find at St. George Crater, and one of which is whether it's crystalline or a breccia type. And anorthosite is what we might expect to find. We spent a great deal of time at Duluth looking at it, but we didn't get to run an EVA exercise, and that's what I think is beneficial to start out, and that's what we've been doing for over a year now, is we take the cameras and the Capcom and the radios and the tongs and the bags, and we go out.
With all this advanced communication and everything that this mission, we're going to get to see and hear probably more of the moon than ever before, hear more about it. And are you going to see to it that people sitting at home watching on television know what's going on out there, a running commentary type thing? If you're interested in geology anyway, why, that'll be fairly easy to...
Yeah, well, indirectly, yes. I think our running commentary will be for the people in the back room, the geologists in the staff support room. And I think that will tie in with what you see on television. However, they are operationally separated from one another. The television is remotely controlled from the ground, and there are certain priorities on what the television looks at during any planned stop. And these are all worked out. And about all we're going to do with the television is indicate the direction in which we're going at any particular stop, so when they finish their pans and everything, they can come and find us and track us. But as far as trying to pick up a rock and hold it in front of the television camera and describe it, no, we don't have any plans to tie in with the TV specifically, because it would detract from what we're trying to do, to select the samples and analyze the geology. It really would, to try and talk at a level at which we could be understood by the general public. See, we've got to talk to the geologists, because it's their interpretation of what we see which will enable all of us to make on-the-spot decisions to get the most out of the flight. So we're not going to be able to run a commentary for the people back home. That's going to be up to people like you to explain what's going on.
Do you expect to be able to pick up a rock and say that's a breccia, and maybe I ought to go over here and look for a piece of granite or basalt?
Oh, yeah, we've spent a great deal of time with the 12, 13, and 14 rocks. 11, 12, and 14 rocks. As a matter of fact, we have a session Monday, and we go into LRL and do this with the big ones, and it's pretty good. But I think now there's a certain question as to what you can see through that visor.
Yeah.
And the guys have had trouble seeing things with the rocks, and we're sort of saying, well, we hope we can see something, but guys have had trouble seeing through that visor, and you sort of have to keep it down. And we may be limited merely visually as to what we can see, but we can tell you which ones are angular and which ones are rounded, kind of thing. But I hope we can give you a fairly good description of what we're seeing. We're going to attempt to do that.
This is Kennedy Launch Control, T-minus 2 hours and counting. T-minus 2 hours and counting, and all going very well with our countdown here in Apollo 15. The crew here in Firing Room 1 is monitoring the status of the various propellants on board the Saturn V rocket, while the astronauts in the spacecraft at the 320-foot level at the pad now busy performing some final checks before the hatch will be closed on the cabin. The spacecraft commander, Dave Scott, coming up shortly on one of our major milestone checks. This is a check of the emergency detection system on board the vehicle. The emergency detection system senses initial development of conditions which could cause a launch vehicle failure and relays this information via cue lights or abort lights on the commander's panel, Dave Scott's panel on the left-hand side of the spacecraft. Our countdown has been going excellently since it picked up at 11:34 p.m. last evening. We've loaded more than 750,000 gallons of liquid oxygen and liquid hydrogen aboard the 3 stages of the Saturn V launch vehicle. We have had no problems during the count, and all has gone well. The prime crew for the mission, astronauts Dave Scott, Al Worden, and Jim Irwin, were awakened as planned in the countdown at 4:19 a.m. Eastern Daylight Time. A short time later, Dr. Jack Teagan came by the crew quarters and gave them a brief physical examination, declared them physically fit and very well rested. The astronauts then sat down to breakfast. They had 6 guests for breakfast in the crew quarters this morning. The menu was the usual astronaut fare on launch morning of orange juice, eggs to order, tenderloin steak, toast, and coffee. Joining the astronauts for breakfast were their boss, astronaut Donald Slayton, who also was the man who awakened them at 4:19 a.m. Also at the breakfast table was Vance Brand, the backup command module pilot, and scientist astronaut Jack Schmidt, the backup lunar module pilot. These two men, of course, have worked very closely with the prime crew over the many months of launch preparations. Also, one of the key members of the support team for this mission, scientist astronaut Dr. Joe Allen, also joined the crew for breakfast, along with the administrative head of the crew quarters here at the Kennedy Space Center, Harold Collins, and Mr. Jim Smotherman, who is the training director for the Apollo 15 crew operations. Following breakfast, about 45 minutes after they began their breakfast, the crew went down the hall at the crew quarters to the suit room to don their pressure suits. They departed from the crew quarters on time as far as the countdown is concerned at 6:28 a.m. Eastern Daylight Time and took the 18-minute ride to the launch pad, a trip of about 9 miles from the crew quarters to the launch pad itself. They then boarded the first of 2 elevators that took them to the 320-foot level, the location of the spacecraft hatch. The astronauts went aboard in a 15-minute sequence starting at 6:53 a.m. this morning when the spacecraft commander, Dave Scott, went aboard and took his seat on the left-hand side. Next to go aboard, the lunar module pilot, Jim Irwin, at 6:58 a.m. Jim Irwin sits on the right-hand side of the cockpit. And finally, the third member of the crew, Al Worden, the command module pilot, took his seat in the middle between Scott and Irwin. That's our status at the present time as our countdown proceeds. The astronauts busily checking out systems on board the spacecraft. We note the hatch now has been closed, and the closeout crew will now begin the purge sequences to bring the cabin atmosphere to the planned 60-40 combination, 60% oxygen and 40% nitrogen for liftoff. The astronauts, of course, are breathing pure oxygen through their spacesuits. Weather conditions are very satisfactory for launch attempt this morning. The forecast is for clear to scattered clouds in the Kennedy Space Center area. Surface winds here at KSC are from the south at about 5 to 10 miles per hour. We expect a temperature of about 83 degrees. The weather around the worldwide track as far as the first few hours of the flight are concerned, also very satisfactory. In fact, one of the contingency recovery ships, the USS Austin, which is located 520 nautical miles off the coast here from the Kennedy Space Center, reports that in their area the seas are calm. They have winds about 4 knots, a 5/10 cloud cover, and 10-mile visibility. All is go for the mission. Dave Scott now beginning this lengthy series of checks of the key emergency detection system, working with the members of the launch vehicle team here in the firing room and the spacecraft team located in their control room back at the Kennedy Space Center Manned Spacecraft Operations Building. 1 hour, 55 minutes, 45 seconds, and counting. This is Kennedy Launch Control.
At Cape Kennedy today, everything was reported going smoothly in the countdown for Monday's launch of the Apollo 15 moon mission. During the night, work crews eliminated what could have been a serious problem when they discovered and replaced a faulty battery in the landing module. There's been some concern about frequent thunderstorms in the Cape area, but forecasters say there should be satisfactory weather at liftoff time. From ABC Science Editor Jules Bergman, a report on the mission.
This will be the heaviest Apollo spacecraft ever launched, 3 tons heavier to carry the extra supplies and the lunar rover for the longest Apollo mission ever attempted. The lunar module itself is the first of the extended LEMs to support the astronauts for the long 3 days and nights they'll spend on the moon. The landing site, Hadley Rille, a huge gorge or canyon, expected to tell us far more about how the moon began. The Falcon lunar module will soar down in a steep descent over 15,000-foot mountains, aiming for a landing in a high plateau a mile from the edge of the Rille. The Rille itself, 80 miles long, up to a mile wide, and 1,200 feet deep. It's similar to the Grand Canyon. Astronauts Dave, Scott, and Jim Irwin will carry 4 times the scientific experiments of any past Apollo flight. By drilling into the moon and planting sensitive thermometers, they'll get the data on how hot the moon is and how fast it's cooling, clues to how it began. The secret to the mission is the Lunar Rover, a 6 by 10-foot lunar dune buggy, aimed at carrying Scott and Irwin up to 5 miles away from the LEM. They'll cover a total of more than 20 miles. The 3 EVAs last 20 hours. The backpacks have been extended for more life support, and the astronauts wear a new, more mobile pressure suit. The Rover enables them to cover 10 times as much distance as they could on foot. It scoots around at speeds up to 8 miles an hour. For the first time, we'll see the astronauts working away from the LEM. The Rover packs its own color TV camera, and each time the Rover stops for the astronauts to work with experiments, the camera will be turned on, and the Rover's own transmitting station will send the pictures back to Earth. During a practice session, we rode the Rover with spacecraft commander Dave Scott.
What do you think of the Rover yourself? Is it a lunar dune buggy or just a Rover or what?
Well, I guess you could call it a lunar dune buggy. It's very mobile, and it's built to go over all the lunar terrain, we might call it. I feel it's really giving us a tremendous advantage as far as being able to, for the first time, really explore a number of different geological settings at one landing site.
This is man the explorer coming into his own really for the first time on the moon.
Yes, I think we're able to now extend our range to where we can take advantage of the many capabilities we have, primarily the extended stay.
Apollo 15, longer, tougher, more dangerous, and far more scientifically rewarding. And Scott, Irwin, and Worden hope that public interest in the space program will be reawakened with their mission. This is Jules Bergman, ABC News at Cape Kennedy. This is Kennedy Launch Control, 1 hour, 51 minutes and counting. All still go with Apollo 15. Spacecraft Commander Dave Scott now busy starting this key emergency detection system test as our countdown continues. Here in the control center, we're making some computer checks of the flight computer on board the Saturn V launch vehicle, located in the instrument unit, which is atop the 3rd stage. All aspects of the mission are still going well. 1 hour, 50 minutes, 30 seconds and counting. This is Kennedy Launch Control.
There it is on the enormous countdown clock overlooking pad 39. T minus 48 hours and holding. We're in one of several built-in holds as Apollo 15 counts down toward 9:34 a.m. Eastern Time Monday, and it's launched to the mountains of the moon. Launch day weather looks good, though we've been having a series of violent Florida electrical storms here, so far with no damage to that towering Saturn rocket. Astronauts Dave Scott, Jim Irwin, Al Worden spent the day in simulators, rehearsing again for their voyage to the moon's most rugged mountain range, the 15,000-foot-high lunar Apennines, and the mysterious Hadley Rille, a mighty gorge 1 mile across and 1,300 feet deep. In their 67-hour stay, almost twice as long as previous Apollos, Scott and Irwin hope to learn what causes such great chasms on the riverless moon. Up there at the top of the rocket, men are now loading liquid oxygen and hydrogen for the two spacecraft, Endeavour, the command ship, and Falcon, the lunar module. Within the lunar module is still a third spaceship, the most interesting of all, because this one has wheels. I drove it here at the Space Center a few weeks ago.
This is the lunar roving vehicle, which is the big difference in this flight of Apollo 15 from all others. This will vastly expand the area which the men can explore on the moon's surface. It means that they can explore 28 square miles, twice as much as previous astronauts have been able to do walking on the surface.
This is the control throttle and wheel, in a sense, for the vehicle. It's a single-handed device. Press it forward. Just doesn't have much throw there. Just press it forward a little bit, and that moves the vehicle forward. It's the throttle and the direction indicator. Bring it back, and it's reverse. Pull it over to the left, and it turns you to the left, and over to the right, and it turns you to the right. Most ingenious device, and a very easy one for an astronaut to handle with the heavy gloves and the spacesuit that he will be wearing. The vehicle moves at about 8 miles an hour. Isn't that right, Don? That's correct. This is that's a good enough speed on the surface. Now, as you know, on the moon's surface, there isn't the same sort of magnetic field that we have here on Earth. Earth compass won't work. Well, believe it or not, with all of these millions of dollars being spent on the space program with this highly sophisticated equipment, an old-fashioned sundial, basically, is what they're going to use in one of the inputs to determine their position. They set this up with the sun behind them, and the sun's at a very low angle on the moon. The sun rays cast a shadow from this bar onto this grade scale here. There's the television camera, that device right over there. It's remote controlled. It means that with this vehicle, we're going to be able to get pictures of a much wider area of the moon than we ever did before.
This factory demonstration shows how, when the astronauts yank lanyards, Rover will unfold itself from the lunar module like a Murphy bed. She comes down back end too. So the first thing Scott and Irwin must do is back up, just like pulling out of the garage in the morning and into the street. Those basket weave metal wheels are what engineers hope will be the best answer to the brand new problem of traction on the moon. Front and rear wheels can steer independently, and each wheel has its own little quarter-horsepower electric motor. Scott and Irwin rehearsed for their moon ride with a rubber-tired Rover in New Mexico, the Rio Grande Gorge being the closest earthly approximation of the Hadley Rille at the foot of the lunar Apennines, where they'll be driving next weekend.
We'll be back with a preview of Apollo 15's ride on the moon beginning at 10:45 tonight Eastern Time over many of these stations. This is Walter Cronkite, CBS News at the Canary
This is Kennedy Launch Control, T-minus 1 hour, 41 minutes and counting. All aspects of our countdown still go for Apollo 15. Spacecraft Commander Dave Scott has wound up his rather extensive test of the emergency detection system, working with members of the launch vehicle and spacecraft team. At this point, the closeout crew members at the 320-foot level, who closed the hatch some 30 minutes ago, now report that the cabin has been purged. The cabin is stable, following some leak checks, and we have the proper environment on board for liftoff. The closeout crew now will proceed to put on the boost protective cover, the protective covering that goes over the hatch for flight. They'll be pulling out, perhaps in about 40 minutes or so, prior to the time that the Apollo access comes back to position some 6 feet from the spacecraft. In the meantime, here in the Launch Control Center, the launch team here working with Mission Control in Houston as some commands are being sent directly to the launch vehicle flight computer located in the instrument unit. These tests also going well, as all aspects of the count have gone since it was picked up shortly before midnight as far as the final countdown is concerned. T-minus 1 hour, 39 minutes, 38 seconds and counting. This is Kennedy Launch Control.
What would it be like to be on the moon? A question that has intrigued men since long before the invention of the telescope. To travel across the roughly marked surface of our nearest neighbor in space is an experience that men will soon be having. Probably before this decade is over, the first explorers from Earth will have arrived on the moon. But how will they explore a planet without roads, without atmosphere, with gravity only 1/6 that of Earth? Scientists are studying answers to these questions. First, by gathering information on the conditions that will likely be found on the moon, then by developing new concepts of travel for vehicles such as we have never seen on Earth to cross terrain that is unique to the moon. The research starts in a laboratory. Here, the vacuum conditions found on the moon are studied for the effect they will have on lunar soil. The large bell jar has been pumped down to a very high vacuum. Inside is a device that is designed to measure the strength of soil. At its base, there are 2 discs of different sizes and an annular ring. The discs are pushed straight down into the soil, and both the vertical force applied and the penetration are measured. This tells something about how much weight the soil will be able to bear. In this case, the soil used is pumice, which is believed to be similar to certain lunar soils. A second test involves the annular ring, or shear ring, as it's called. A known load is applied at the top, and then the ring is twisted. The horizontal force being developed and the angle of rotation are both measured. This tells us something about the amount of traction a vehicle can develop. Here, the same test is shown being applied to a gravel soil under similar conditions. Another effect which is studied is that of low gravity, here being tested on a free-falling device known as an Atwood-type machine. It reveals what happens to a soil in gravity only 1/6 that of Earth, where 100 pounds weighs only 16. Here, a soil test disc is shown being attached to a release. When the test is actually run, this disc will be released into a capsule of soil which is falling at an acceleration which simulates the low lunar gravity. The entire device is raised high into the air, then dropped. During the drop, though so rapidly it could not be seen, the soil test disc is released and the effect of low gravity on soil is measured. Based on such tests of soil properties, several vehicle models designed for moon travel were developed. Here is a vehicle based on the Archimedean screw principle, propelled by the turning of 4 large screws. This wheeled vehicle rolls on 6 large, soft tires arranged on 3 axles. And this track-type vehicle is composed of 2 units with wraparound tracks. These vehicles were tested in a soil bin, containing soils of a type likely to be encountered on the lunar surface. Here, the tracked vehicle is made to crawl over simulated dunes of fine pumice. The wraparound tracks are elastic, with flexible prongs to conform to the terrain while steering at the pivot between the units. The Archimedean screw vehicle is designed to operate only where the soil is so soft that it cannot support the weight of a vehicle. Hence, it burrows through the soil. It is steered by running the various screw elements at different speeds, managing slow but effective turns. The electric cord trailing behind it is used to deliver power to the model. It is not intended for actual moon vehicles, which will use batteries or fuel cells. Generally, the screw principle is not very efficient and would be used only for special applications, such as this exceedingly soft soil. The wheeled vehicle is mechanically the most efficient and reliable of the 3 designs. While it cannot perform as well as a track on soft ground, its many other advantages make it an attractive solution to the problem of an all-around moon vehicle. This particular model has 3 axles or units, individually driven by 3 separate electric motors. The axles are connected to each other by elastic rods, which enable the units to dip and roll with respect to one another. Steering is accomplished by the small steering motors mounted on the front and rear units. The wheels shown on this model are made of foam rubber, but this would not be the case for a real moon vehicle, since foam rubber could never endure the severe lunar temperatures. Instead, a full-size design might feature lightweight wire frames, which would be covered with a thin, tough plastic material. In case the lunar surface does not turn out to be a fine dust, but instead consists of a rough and rocky terrain, the wheeled vehicle will perhaps show itself to its best advantage. The individually powered units have good obstacle climbing ability, even when the obstacles are more than twice the height of the wheels. The vehicle can force itself over and around boulders, yet always hug the terrain because of its special design, which is called articulated. If obstacles such as chasms occur, such as the space between boulders, the vehicle will bridge the obstacle with its long body. Where one unit has lost traction and cannot pull, the others will push it along. In turn, if they lose traction, they will be pulled along, so that the vehicle remains in motion whatever the soil or terrain. In general, the wheeled vehicle seems a promising solution to the problem of moon travel. Yet much work remains to be done. Further and more realistic testing in the moon environment must still be accomplished. New moon vehicles will be conceived, designed, and put through their paces so that the astronauts of tomorrow will have the vehicles to carry them safely to the farthest reaches of the moon.
Kennedy Launch Control, T-minus 1 hour, 31 minutes and counting, all still going well with Apollo 15. The astronaut crew on board the spacecraft at the 320-foot level, still working on their final checks, working with spacecraft test conductor Skip Chauvin. Chauvin just a short while ago instructed the pad leader to start breaking up the white room. This is one of the final processes before the crew is moved. The closeout crew departs from the spacecraft area. The closeout process at this point is to remove certain panels so that the swing arm will be able to come back without any problems at the 43-minute mark in the count. This is swing arm 9, the Apollo access arm, which is first moved some 6 feet away from the spacecraft. Here in the control center, we're getting into some checks of the tracking beacons on the Saturn V launch vehicle, and the checks both here in the firing room as far as launch vehicle and in the spacecraft control room still going very well. 1 hour, 29 minutes and counting. This is Kennedy Launch Control.
Center, Florida, in late July. Here, they summarize their feelings about space and this mission. Who will fly the 12-day mission? Dave Scott, the man in charge on Apollo 15. This will be Scott's third space flight. He flew previously on Gemini 8 and Apollo 9. Launch from the Kennedy Space Center. The crew of Apollo...
The landing site for Apollo 15 at the Hadley Rille is a very dramatic site. We feel that it'll be quite spectacular when you get to see it on television while we're there. It's essentially on a flat plain surrounded by mountains on one side and a rill, or a meandering gorge, we might call it, on the Earth on the other side. The mountains to our east and north and south range anywhere from 11,000 to 15,000 feet high. And the rill, or the gorge in front of us, is like a canyon, and it's about 1.3 kilometers across and 1,000 feet deep. So it's...
Lunar Module Pilot Jim Irwin, 41.
On EVA-1, for instance, we'll be going down to the front first, doing our geology investigation down there along the Apennine front and then over to the rill. And then coming back to the LEM, we'll be unstowing the ALSEP packages and then deploying the ALSEP about 300 to 500 feet west of the LEM. I'll be doing the bulk of the deployment while Dave is doing the drilling operation.
Scott and Irwin are on the surface. 39-year-old Al Worden, Command Module Pilot. A satellite to be placed in orbit around the moon shortly before the crew heads earthward. The sub-satellite should stay in lunar orbit for a year.
The sub-satellite is what I would term a passive experiment. And when I say passive, I mean in the sense that it's not powered in flight. We eject the sub-satellite from the command service module. It goes into an orbit which is then only perturbed by the gravitational attraction of the moon. The sub-satellite is a particles and fields satellite. The main effort in this particular satellite is to measure the particles field around the moon, such as the plasma flow, solar rays, magnetic field, magnetic particles, and this type of thing around the moon.
Scott and Irwin will travel farther and gather more samples for scientific study than any moon landing team so far. They will be able to do this because of the Lunar Rover, a four-wheel battery-operated vehicle.
The television has been developed to be carried on the rover and controlled remotely from the ground. So every time we make a science stop, we enable the television within the communication systems on the rover, and the ground will be able to point the TV in any direction within 360 degrees, elevate it and depress it, and also zoom it. So you'll perhaps have a better view of many things than we will, because you'll be able to watch both of us at the same time.
As they travel toward the moon, a panel door on the side of the service module will be jettisoned, exposing the cameras and scientific instruments, 10 in all. A mapping camera. At the Manned Spacecraft Center, Houston, Worden practiced this maneuver underwater. We asked him to describe his planned trip outside the spacecraft.
Once the hatch is opened, we'll take the TV camera and the 16mm data acquisition camera, mount that on the hatch, the command module hatch, with both cameras pointed toward the service module where I'll be working. Once that's accomplished, then I'll go very slowly down the handrails to the service module, staying away from the reaction control system engines or quads, which are just off the side of the path of the EVA. Go down to the service module, get situated in the EVA restraint boots, which are located on one side of the service module. And once in that position, then I'll remove the thermal and contamination covers from the pan camera cassette first. Once they're removed, I'll pull the cassette out of its bay, tether it to the left wrist, and then very slowly come back the handrails, back to the command module, stow the cassette inside the command module, where Dave Scott will keep track of it and hold it until the end of the EVA.
is Kennedy Launch Control. T-minus 1 hour, 21 minutes and counting. All aspects of the countdown still go for Apollo 15. Still aiming toward our planned T0 and liftoff at 9:34 a.m. Eastern Daylight Time. The administrator of the National Aeronautics and Space Administration, Dr. James Fletcher, has just arrived here in Firing Room 1, the control room for this launch. He is being briefed by the Deputy Administrator, Dr. George Lowe, and is being told that the countdown is still going excellently, as it has since it picked up late last evening. The spacecraft commander, Dave Scott, aboard the spacecraft with his two comrades at the 320-foot level at the pad. Scott now working on some command and guidance checks, working with spacecraft test conductor Skip Chauvin and the spacecraft checkout team. Here in the firing room, under the direction of Test Supervisor Jim Harrington and the launch vehicle test conductor Norm Carlson, the launch team making some final telemetry checks of the status of the tracking telemetry in the 3 stages and instrument unit of the Saturn V launch vehicle. Still counting, still go. Weather report excellent for a launch attempt. A beautiful morning for a flight to the moon. 1 hour, 19 minutes, 45 seconds and counting. This is Kennedy Launch Control.
all these things.
There we are. Now we're in the suit itself. Because the suit is so heavy, it gets very warm inside. So these connections that you see right here are to get air or oxygen in and out of the suit to keep us cool and to give us air to breathe. So what we'll do now is put the air into the suit so that I'll stay cool. And I'll probably be cooler than you.
You mean all this is filling up with cool air now?
It's all filling up with cool air, right.
And what's
now,
this?
we'll put the telephone on.
The way you'll be in touch with us.
That's right.
Here on the Earth.
You can see, let me show this. There are two earphones, one on each side, and two little microphones. And it's just like having two telephones, one on each side of your head, except that this telephone here is fastened to my head.
This is the part that you speak into, right?
That's right, yes. Speak right into this part, and just here with this part. And now I don't have to touch it, see? It just stays on there by itself. You can see that wire now is connected into my suit. The other end of this wire comes out right here, and I have another wire that hooks into this that goes in to the inside of the spacecraft.
See.
Once we get this far, then we go ahead and put on gloves and a helmet to wear, and let's go ahead and do that. This is a helmet.
Now you can breathe in there, can you?
This is Kennedy Launch Control, T-minus 71 minutes and counting. 71 minutes and counting, all still proceeding very satisfactorily with the countdown for Apollo 15. Spacecraft Commander Dave Scott, who sits on the left-hand side of the spacecraft, still very busy on board working with spacecraft test conductor Skip Chauvin as they make final checks of the guidance and stabilization control systems aboard the Apollo spacecraft. As a part of this test, Dave Scott actually will send commands to cause that big engine below them in the service module to swing or gimbal in response to commands from the guidance system. The service module propulsion system, which is capable of some 20,000, 500,000 pounds of thrust, is used for all the major maneuvers on the flight to and from the moon once the big Saturn V launch vehicle has done its job and placed it on the proper trajectory toward the moon. Here in Firing Room 1 are checks of the various telemetry systems and calibration of telemetry. The tracking information we'll receive from the vehicle is still continuing. We'll also be coming up shortly on some more checks of the tracking beacons on board. We have been alerted that the swing arm, the Apollo access arm at the 320-foot level, may come back about 10 minutes earlier in the count because the count has been going so well and we've been a little bit ahead on many of the procedures. The closeout crew, who have been aiding the astronauts at the 320-foot level, have completed their job and have now departed. That's our status. All is go. 79 minutes, 20 seconds, and counting. This is Kennedy Launch Control.
I met astronaut Worden in the launch room of the Kennedy Space Center, the room which is filled with some of the machinery that helps rockets get started to the moon.
I'm very happy that you're here.
May I just launch right into the questions?
Certainly.
These are questions that reflect children's concerns about exploration in space.
Well, they're probably the same concerns that everyone has, friend.
Did anybody say you had to fly to the moon?
No, nobody said I had to fly to the moon. It was my own choice to come in the program. Once I was in the program, then assigned to a crew, then it was no longer my choice. I was on that crew, and I would go to the moon on that crew. But to come into the program was my choice.
Did you have a mother and father when you were a little boy?
Yes, I certainly did have a mother and father, and I still do, and they're still living in Michigan. And so are my brothers and sisters. I've got 3 brothers and 2 sisters living there.
One child wanted to know, do little children ever go to the moon?
No, we don't have any little children yet that we would take to the moon. And in fact, we don't have any ladies yet that go to the moon. I think someday we will send ladies and we will send children.
So many children wondered whether those suits that you wear are heavy, and do you need people to help you get dressed in those suits?
The spacesuits are very heavy. In fact, the suits weigh about 70 pounds. You have to have somebody help you into the suit because the suits are very tight-fitting. They have a very tight zipper on them, and they're very difficult to get into, so we have to have somebody help us on with the suits.
Al, I'd like to know for myself, do you wear those spacesuits all the time during the flight?
No, we only wear spacesuits when there's any question about keeping our atmosphere around us inside the cockpit of the spacecraft. So we wear it during launch, and then we wear it anytime we're going to open a hatch or we're going to go between our spacecraft and the one that's going to land on the moon. The rest of the time during the flight, we wear just a set of coveralls. They're lightweight coveralls that we wear over our constant wear garments. A constant wear garment is just a fancy name for long underwear, and we wear those when we're not wearing a spacesuit.
How do you go to the potty when you're flying to the moon? A very young friend of mine asked that and was concerned about it.
Well, I think that's a very, very good question. And bless children for asking the question, because sometimes grown-ups don't like to ask those sorts of questions, and I think children are honest and open enough so that they'll ask that kind of a question. But we go to the potty on the way to the moon and back, just like we do here on the ground. The only difference is that when we make a BM, we collect it in a plastic bag, and we save it, and we bring it back with us. But other than that, it's exactly the same as here on the Earth.
Now, one child wanted to know, do spacemen ever get thirsty?
Oh, yes, we get thirsty all the time. And in fact, probably not known by a lot of people is that we make our own water as we go. The equipment that supplies us with electrical energy to run all the systems that we have produces water. And we collect that water and we drink that water on the way out to the moon and back.
One child said, how do you think he'll feel when he splashes down in the water?
I really haven't thought that much about it, but I think I'll feel sad that the flight's finished. I think I'll feel happy that we've been there and we're back, and I think I'll be awfully glad to see somebody.
One child said, do astronauts ever cry?
I think that I'd have to answer that particular question in 2 ways. One is in the part of an astronaut that you see, when you see one on television, when you watch a launch, that part of that astronaut doesn't cry. He's doing a job, and he is not sad about it. There's nothing to cry about, so he doesn't cry. But I think once he's home, and once he's involved with other people and with children, if something should come up to make him sad, certainly he'd cry.
Al, one more question from a child, and that was, why do people go to the moon?
That is a question that we've all thought about a great deal, and I guess from my own standpoint, we go to the moon so that we can learn more about ourselves. We learn more about Earth, we learn more about the moon. We want to find out more about how to make people comfortable and how they can learn about themselves and about the things around them more. And that's one of the reasons we go to the moon, is so that we can make the Earth a better place to live.
This is Kennedy Launch Control, T-minus 61 minutes and counting. T-minus 61, the countdown still proceeding very satisfactorily. Now just a little more than an hour away from our planned liftoff here on the Apollo 15 mission. Astronaut Dave Scott, who will be making his third space flight, is still working with the spacecraft test conductor in the spacecraft cabin at the 320-foot level at the pad, working with spacecraft test conductor Skip Chauvin back at the control room. We have completed our final guidance alignment checks of the spacecraft systems, and we're now making some final checks of the entry monitoring system, the system that would help guide the spacecraft back in on a re-entry from a trip from the moon, and also, of course, if there was an emergency condition where the spacecraft had to come back in. Skip Chauvin has just advised the astronauts that the swing arm, which is now still attached to the spacecraft, probably will be coming back in about 7 minutes from this time. The swing arm is moved to a position about 6 feet away from the spacecraft, so that if there was an emergency condition where the astronauts needed to egress the spacecraft in a hurry, that swing arm could be brought back in a matter of seconds so that the astronauts could get out. At the 5-minute mark in the countdown, the swing arm is retracted to its fully retracted position at the pad. Here in the Launch Control Center, our telemetry calibration checks are still in progress. We'll be making some checks of the Range Safety Command Destruct system aboard the vehicle, the system that would be used to destroy the vehicle after an abort sequence had occurred and the astronauts had escaped from the vehicle in trouble. That's our status. All is go. 59 minutes, 10 seconds and counting. This is Kennedy Launch Control. This is Kennedy Launch Control. We're at T-minus 56 minutes and counting. All still going well with the countdown at this time. Coming up in just about 3 minutes, that Apollo access arm, the arm that the astronauts used to go across to board their spacecraft, will be retracted to a standby position. It's retracted 12 degrees or some 6 feet from the spacecraft. Once this does occur, we arm that launch escape system, the launch escape tower on top of the spacecraft, and from that point down in the countdown, if there was any critical emergency situation, an abort could take place right on the launch pad with the solid fuel motors in the launch escape tower, which generates some 155,000 pounds of thrust, pulling the spacecraft away from a launch vehicle that would be in trouble and an explosion imminent. This is one of the number of emergency conditions that we do plan for and do have systems to handle here in the last hour or so of the countdown. All aspects of the count still going well. We're at 54 minutes, 45 seconds and counting. This is Kennedy Launch Control. This is Kennedy Launch Control. The swing arm is now moving back from the spacecraft on command right at the 53-minute mark. It'll be moved some 6 feet away from the spacecraft and remain in that standby condition for contingency purposes through the remainder of the countdown until at 5 minutes it is fully retracted. The astronauts, of course, were alerted that this event would occur because they do feel a slight jolt as the swing arm and the white room attached to its tip is pulled away. The astronauts still continuing their final checks aboard the spacecraft, and the crew here in firing room 1 at the Launch Control Center here at Complex 39 still monitoring the status of the propellants on board the vehicle. We loaded more than 750,000 gallons of liquid oxygen, liquid hydrogen aboard the Saturn V this morning from the time the countdown picked up late last evening. A power transfer test, one of our key tests over the last hour or so in the countdown, has been successfully accomplished here in the firing room. We have switched from external power to the internal batteries on board the 3 stages and instrument unit of the Saturn V to assure that they are operating properly. To conserve those batteries on board, we've now returned to external power. We will finally switch internal with the rocket at the 50-second mark in the count. The countdown has been going very well. In fact, we're about 10 minutes ahead on events both concerned with the spacecraft and the launch vehicle. We're now 51 minutes, 25 seconds and counting. This is Kennedy Launch Control.
During the early Apollo years, NASA scientists and engineers anticipated the need for a vehicle to aid the astronauts in exploring the moon. It was expected that bulky spacesuits, limited life supplies, and other inherent weaknesses would decrease man's mobility on the lunar surface. In 1964, with conceptual design of the Mobile Laboratory, or MOLAB, NASA began research on lunar surface vehicles. Over the next few years, an entire spectrum of vehicles was designed and studied. From these efforts came the knowledge that contributed directly to the development of the lunar roving vehicle. Its development required solution of many challenging technical problems for which there were no precedents in terrestrial vehicle design and operation. For example, the lack of an atmosphere on the moon, the extremes of surface temperatures, plus or minus 250 degrees Fahrenheit, the very weak gravity, 1/6 of Earth's, and the many unknowns associated with the lunar soil and topography. All these factors imposed severe and unique requirements on the LRV. The first manned landing on the moon, Apollo 11, and subsequent missions confirmed the long-recognized need for a lunar vehicle, a vehicle which would allow astronauts to cover more area, to conserve energy and life support materials, to transport additional equipment, and to return with more lunar soil samples. For even before these practical demonstrations, in May of 1969, NASA decided to proceed with the design and development of a lunar roving vehicle. The Marshall Space Flight Center at Huntsville, Alabama, where the Saturn V moon rocket had been developed, was assigned overall direction of the LRV program. Prime contractor was the Boeing Company, using facilities at Huntsville and Kent, Washington. Major subcontractor was GM's Delco Electronics Division in California. The LRV would be a two-man, four-wheeled vehicle, 10 feet 2 inches long, 44 inches high, with a 7.5-foot wheelbase, weighing 460 pounds earth weight, and capable of carrying a total payload of 1,080 pounds. The LRV would have 5 major systems: mobility, cruise station, navigation, power, and thermal control. The mobility system, which must be able to cross 12-inch high obstacles and 28-inch diameter craters, consists of the wheels, traction drive, suspension, steering, and drive control electronics. The system was designed, developed, and tested by General Motors. The first assemblies were put through development tests to measure strength, deflection, endurance, and other factors. For example, driven on a rolling road fixture, the wheel assembly was tested under Earth conditions, and later in test chambers reproducing the environmental conditions of the moon. The LRV tires are made of a woven mesh of zinc-coated piano wire, to which titanium threads are riveted in a chevron pattern to keep the wheels from sinking into the soft lunar soil. Long-duration torture testing on this so-called carousel, simulating the lunar surface, verified the durability of the wheel design. The test assembly was supported by springs to relieve most of its weight, thus simulating the 1/6 gravity of the moon. A mobility test unit was used in early phases of development to validate the LRV mobility system. The astronauts participated, as they did in all aspects of LRV development. 2 36-volt silver zinc batteries provide the vehicle's power. Each wheel is individually powered by a 1/4 horsepower electric motor. A highly efficient harmonic drive system, originally developed by the U.S. Shoe Machinery Corporation for other purposes, is used with each motor, eliminating the need for a transmission and its gears. The suspension consists of a damper or shock absorber supported by triangular arms that pass the suspension loads to torsion bars. Other systems were also being developed. For example, a simple navigation system, which would allow astronauts to drive beyond sight of a lunar module and yet be able to return to it by the most direct route.
This is Kennedy Launch Control, T-minus 46 minutes and counting. T-minus 46 minutes and counting. We are proceeding satisfactorily, aiming toward our planned liftoff here for Apollo 15. The Apollo 15 astronaut crew standing by in the spacecraft at this time. They'll have quite a bit more work before we reach our T0, but they're standing by at this point. They've completed their guidance and alignment checks and are waiting as certain key launch vehicle checks are taking place at this time. We have just completed a check of the Digital Range Safety Command Destruct System. These are the destruct packages aboard the 3 stages of the Saturn V that would be activated if the vehicle was flying off course and was a danger to personnel below. Of course, before the destruct system would be activated, the abort sequence would take place and the astronaut crew and their spacecraft would be separated from the launch vehicle. Our weather is go and all aspects of the countdown go. 44 minutes, 57 seconds and counting. This is Kennedy Launch Control.
The system works by recording direction and distance traveled from a starting point. In order to assure the proper physical relationship or interface between the vehicle and the astronauts in their pressurized spacesuits, several so-called crew station reviews were conducted, first in normal Earth gravity conditions and later in simulated 1/6 G. The LRV's crew station consists of the control and display console, seats and seat belts, armrests, footrests, hand and toe holds, floor panels, and fenders. For other crew station reviews and development testing, an LRV mock-up was installed in a KC-135 aircraft which flew parabolic flight paths. This provided brief periods of low gravity, simulating lunar conditions. One example of interface problems was the initial difficulty in getting onto and off of the LRV. Addition of a simple tow hold plus astronaut training proved to be the solution. Another interface problem was the design of control switches, which could be easily manipulated by a gloved hand. Similar problems were involved in operation of the uniquely designed hand controller located between the two astronauts, which provides steering, speed, and banking commands to the vehicle's drive control, electronics, and mechanical brake system. A major milestone in the Lunar Roving Vehicle Development Program was delivery by General Motors of the 1G trainer vehicle to be used for astronaut training. Though heavier and stronger than an actual moon rover, since the crew and equipment weigh 6 times more on Earth, the trainer was practically identical in size, shape, and handling characteristics. One simple difference was the use of ordinary pneumatic rubber tires because of the extra weight of the vehicle. At the Manned Spacecraft Center, the 1G trainer was operated using counterbalance springs to simulate the moon's gravitational field. Through operation of the trainer in this mode, astronauts were able to become accustomed to the LRV months before actual use during their mission. Storage and deployment of the vehicle provided major design challenges. As shown here by this special test unit built to equal on Earth the LRV's lunar weight, the vehicle had to fit within the tight wedge-shaped confines of one small section of the lunar module, about the volume contained in a family station wagon. Conversely, on the moon, the LRV has to essentially unfold itself by means of springs and deploy to the lunar surface locked in its operating configuration, all with minimum assistance from the astronauts. Further deployment tests were conducted using a full-weight LRV called a qualification test unit. The vehicle was deployed from a lunar module mock-up at the Grumman Aircraft Company, contractor for the lunar modules. During these tests, technicians manually assisted the vehicle throughout the procedure, since the deployment mechanisms were designed for the moon's weaker gravity and could not overcome the stronger gravity of the Earth. The main purpose of the qualification test unit was to make absolutely sure that nothing had been overlooked in terms of clearances and hardware operation.
This is Kennedy Launch Control at T-minus 40 minutes, 54 seconds and counting. Still proceeding very well at this time, aiming toward our plan T0 at 9:34 a.m. The astronauts will be busy again shortly in the spacecraft, particularly Command Module pilot Al Worden as he proceeds to go through the sequence of pressurizing the reaction control system of the spacecraft. This is primarily concerned with those 4 quadrants of 100-pound thrust rockets on the side of the service module. We pressurized that system before launch, and Al Worden reads off the status of the overall system so that spacecraft test conductor Skip Chauvin and the crew back in the spacecraft control center can determine that that system is go for launch. Of course, the reaction control system used extensively on the flight to and from the moon for small refinements on trajectory. Here in firing room 1, we go for the final portion of the count. We have a clearance from the range to launch, and our countdown is continuing. The countdown has been going excellently since it picked up at 11:34 p.m. last evening following a 9-hour, 34-minute built-in hold. Since that time, a major portion of the count was devoted to the propellant loading of the Saturn V launch vehicle, bringing aboard liquid oxygen and liquid hydrogen, the so-called cryogenic propellant, aboard the 3 stages of the vehicle. We loaded more than 750,000 gallons of the oxygen and hydrogen on board, and at liftoff we expect to have a vehicle weighing close to 6.5 million pounds on the launch pad. The Saturn V space vehicle stands some 363 feet. As far as the Apollo 15 crew is concerned, the crew was awakened by their boss, Donald K. Slayton, as planned in the countdown at 4:19 a.m. Eastern Daylight Time. They were given a brief physical exam by Dr. Jack Teagan a short time later, and he declared them in excellent physical condition and very well rested. The crew then sat down to breakfast with a number of the astronaut members of the backup team and support team who have worked so hard with them in preparation for the mission, and then were ready to proceed to the suit laboratory to don their pressure suits and go through final checks prior to being ready to go to the launch pad. Once again, as planned in the countdown, they departed the crew quarters at 6:28 a.m. Eastern Daylight Time, arrived at the pad about 18 minutes later, and then went on board the spacecraft at about the 2.5-hour mark in the count. Since that time, Scott, Worden, and Irwin have been performing various checks, working with the spacecraft control team, and all these checks have gone well. Our status is excellent at this time. The weather forecast is certainly a go for launch with clear skies or clear to scattered skies. The surface winds about 10 miles per hour from the south, and the weather situation on the worldwide track as far as contingency purposes all go. That's our status, T-minus 37 minutes, 35 seconds, and counting. This is Kennedy Launch Control.
Manufacturing of the first flight LRV proceeded concurrently with the rigorous testing of non-flight units. As evidenced in this wheel fabrication, skilled and detailed handcrafting was involved in many of the LRV components. Early in 1971, production and testing of the first flight LRV neared completion. Vibration tests were conducted with the vehicle in both the folded and unfolded modes to determine critical frequencies. Other acceptance tests checked and rechecked every facet of the vehicle. The first flight model LRV was formally delivered to NASA by the prime contractor, Boeing, on March 10, 1971, 2 weeks ahead of schedule. It had been less than 18 months since inception of the LRV program, only 13 months since the prime contract was awarded, an accomplishment reflecting the outstanding effort and dedication of the joint NASA Industry Development Team. After government acceptance of the vehicle, it was folded, covered, and crated for shipment to the Kennedy Space Center. After delivery to KSC, the vehicle was unfolded and completely checked out again, and another crew station review was conducted. The LRV was then folded for the final time and installed in its flight position inside the lunar module of the Apollo 15 spacecraft, several months before launch. The LRV had received its final go, while the rest of the Apollo and the Saturn V launch vehicle would undergo further checkouts.
This is Kennedy Launch Control, T-minus 31 minutes and counting. T-minus 31. Our mission with Apollo 15 still go. This is the fourth flight intended for a lunar landing, and all is going well. We're still aiming toward our plan T0 at 9:34 a.m. Eastern Daylight Time, when, if all goes well, those 5 big engines in the first stage of the Saturn V will ignite, generating more than 7.7 million pounds of thrust to start us on the way on a long trip to the moon. 30 minutes, 25 seconds and counting. This is Kennedy Launch Control. This is Kennedy Launch Control, T-minus 26 minutes and counting. We're still proceeding very satisfactorily here in the final minutes of the countdown, all still going well. The busy activity right now, astronaut Al Worden giving final verification of the status of the propellant system on board the Apollo spacecraft. He's working with spacecraft test conductor Skip Chauvin, giving the key readings on the various systems, temperatures, and pressures to assure that that reaction control system is go for the launch. It will have a lot of work to do during the mission, and we want to make sure that it is precisely right before we're ready to commit to launch. Skip Chauvin now informs the astronauts that we're still about 10 minutes ahead in the countdown, and Dave Scott replies back with a rather quick roger. The countdown's still going. Launch vehicle status is go. 25 minutes, 2 seconds and counting. This is Kennedy Launch Control. This is Kennedy Launch Control, T-minus 20 minutes, 56 seconds, and counting. All aspects of the count still go, still aiming toward our planned T0 at the appointed time of 9:34 a.m. Astronaut Al Worden, the command module pilot in the middle seat, has completed his checks of the pressurization system for the reaction controls of the Apollo spacecraft, and all is still going well. Here in the Launch Control Center, the crew has started a sequence to chill down the upper two stages of the Saturn V because of the extremely low temperatures of the liquid oxygen and liquid hydrogen involved in the propellant system, and it is necessary to condition the engine chambers in both the second and third stages so that they will be at a lower temperature when the propellants are introduced at ignition time during the powered phase of the flight. We'll have more than 11 minutes of powered flight in the first phase of the mission before the spacecraft, the Apollo spacecraft, is placed into a parking orbit some 90 nautical miles high, still attached to the third stage. A second burn of that third stage of the Saturn V will place the spacecraft on its proper translunar trajectory. Our status, 19 minutes, 40 seconds and counting. All aspects still go. This is Kennedy Launch Control. This is Kennedy Launch Control. 16-minute mark has just been passed. We're at 15 minutes, 53 seconds, and counting. The astronaut crew standing by for some important functions that will be coming up in a minute or so as the Apollo spacecraft goes on full internal power on the fuel cells on board. Up to this time in the countdown, an external power source also has been applied to conserve those fuel cells. The external power source is removed. The astronauts will take a look at the status of their power system on board and report it back to the spacecraft control center. Both the astronauts also will arm their hand controllers on board the spacecraft, and we will be ready to proceed to also place the emergency detection system on its automatic mode. Our countdown is still proceeding very satisfactorily as we come up on the 15-minute mark. The flight azimuth is the same. About 5 minutes ago, there was an update given to the spacecraft computer. No changes were required because our countdown is right on time. 14 minutes, 53 seconds and counting. This is Kennedy Launch Control. This is Kennedy Launch Control, T-minus 10 minutes, 55 seconds and counting. Countdown still running smoothly as astronaut Dave Scott on board the spacecraft checks out a key abort circuit. This is a special communication system with only about 3 or 4 people on it. These are the people who could recommend an abort to the spacecraft commander if required. These people include the launch operations manager, Paul Donnelly, the spacecraft communicator here in the control center, astronaut Vince Brand, spacecraft test conductor Skip Chauvin, and Houston Flight Director Jerry Griffin. We've checked out this special communication system, and Dave Scott confirms that all is well. The countdown proceeding. Jim Irwin now reading out some checks on the status of the fuel cells as we continue to go. We'll go on an automatic sequence here in the countdown, starting at the 3-minute, 7-second mark in the count. From that time down, we will be automatic with the countdown driven by the computer. This will wind up with ignition of those 5 engines in the first stage at the 8.9-second mark in the countdown. The engines will build up to their full thrust. The computer will make a determination that we have 90% thrust in all 5 engines, and that will be the signal for commit or to release the vehicle. Our countdown is still proceeding, 9 minutes, 33 seconds and counting. This is Kennedy Launch Control. This is Kennedy Launch Control, T-minus 5 minutes, 55 seconds and counting. We're still go. We're about to come up with some status checks now to determine the final status. In the meantime, the lunar module test conductor, Fritz Weideck, has come in over the circuit and informed the spacecraft commander, Dave Scott, that lunar module Falcon and the rover are go. Dave Scott thanked him for this and then also received a report from spacecraft test conductor Skip Chauvin that the command ship, which will have the call sign Endeavour, also is go. We've just completed our status reports, and the launch operations manager, Paul Donnelly, the launch director, Walt Caprian, and the mission director, Chet Lee, all have given their goes. We're standing by for the swing arm to retract to its full fallback position. It's moving now as we approach the 5-minute mark in the count. Coming up on the 5-minute mark. Mark, T-minus 5 minutes and counting. We're go on Apollo 15. This is Kennedy Launch Control. This is Kennedy Launch Control. We've just passed the 3-minute, 30-second mark in the count. The terminal sequencer has been armed, and we are go. Launch Operations Manager Paul Donnelly just wished the crew good luck and Godspeed and received an expression of thanks from all 3 crew members. We'll be coming up shortly on the automatic sequence. 3 minutes, 10 seconds. Firing command enable. Firing command on. We have the firing command. We're now on the automatic sequence. And the tanks in the 3 stages of the Saturn V that contain those propellants will begin to pressurize. The countdown is still proceeding, and we're at now 2 minutes, 50 seconds and counting. We understand there's an estimate that there are more than 1 million people in the area here to view the launch. The traffic has been heavy since 2 o'clock this morning. The beaches are packed and the roads are packed. 2 minutes, 35 seconds and counting. We're monitoring our status board here in firing room 1. Our ready lights are on, concerned with spacecraft, emergency detection system, instrument unit. Our preparations are complete, and the automatic sequence is continuing. 2 minutes, 20 seconds and counting. We now have second stage liquid oxygen and third stage liquid oxygen supplies pressurized as the countdown continues. Coming up on the 2-minute mark, we'll be standing by for the cue ball cover to be retracted shortly atop the Saturn V vehicle. Mark, T-minus 2 minutes, T-minus 2 minutes and counting, still going well. Propellant stable on board the vehicle. The crew here in the firing room monitoring more than 300 red line values, watching temperatures and pressures to ensure they do not go above nominal. In the case that it did, any one of these key people could call in to hold the countdown. 1 minute, 36 seconds and counting, still going well. The pressurization sequence is still continuing in the vehicle. We're now 90 seconds away from liftoff, all still going well. We'll go on internal power with the vehicle at the 50-second mark in the count. We now get indications from our status board that all is still going well, and the third stage is now completely pressurized. Coming up shortly on the 1-minute mark, we're now 70 seconds and counting. Second stage tanks are pressurized as our countdown continues. Mark, T-minus 60 seconds and counting on Apollo 15. The astronauts are go, launch vehicle and spacecraft components all go as our countdown proceeds. Now 50 seconds, we have the power transfer. The vehicle now on the battery power in the vehicle, and all is still going well. Lunar Module pilot Jim Irwin making some final checks, now passing the 40-second mark. Spacecraft Commander Dave Scott now has made his final check, that is aligning the guidance system. 30 seconds and counting. The guidance system will go internal at the 17-second mark. Now 25 seconds. We have complete clearance to launch. We are go. 20. 15 seconds. Guidance internal. 13, 12, 11, 10, 9, 8. Ignition sequence start. Engines armed. 5, 4, 3, 2, 1. All engines running. Launch commit. Liftoff. We have liftoff at 9:34 a.m. Eastern Daylight Time. The tower is clear.
And we have a roll program. Roger. You have good thrust on all 5 engines. Same total. Roll complete. Roger. And we have a pitch program. Roger. Stand by for mode 1 Bravo. Mark 1 Bravo. Roger, 1 Bravo. Booster Systems Engineer reports to Flight Director that S1C stage looking good. Houston, everything looks perfect down here. Okay, looks smooth up here, Gordo. Going through maximum dynamic pressure at this time. Downrange 14.5 miles height. Charlie. Mark 1 Charlie now. Roger, 1 Charlie. Each of the S1Cs. Roger. Each of the 5 S1C engines gulping 3 tons of fuel per second. Inboard. Roger, inboard. Flight Dynamics reports go for staging. Good stage. Roger. Houston, you have good thrust on the S2. All 5 are good. Okay. .73 miles downrange, 47.9 altitude. 7.7. Roger. Fire jet. Roger, we confirm the skirt SEP, you're mode 2. Roger, mode 2. Guidance initiate. Roger. Coming up on 10,000 feet per second mark, downrange 131, altitude 66.
15 Houston at 4. The guidance has converged. The CMC is go. Everything looks good.
Okay, go. Looks good up here.
Now at 35% of the velocity needed to orbit. Downrange 190 miles, altitude 79.
Houston, 5 minutes. Everything looks nominal. Your go.
Okay, good up. Thank you. Looks good up here.
40% of velocity needed.
Roger.
Downrange 271, altitude 88. Predicting nominal shutdown on the S2 stage.
Times are nominal. Level sense arm will be 8 plus 3, 4, and S2 cutoff at 9er plus 0, 9er. Over.
Roger, 8 plus 3, 4, and 9 plus 0, 9.
And stand by for S4B to COI. Mark, you have S4B to COI now.
Roger, S4B to COI.
380 miles, downrange, altitude 94.5. Velocity 15,000 feet per second.
Stand by for S4B to orbit capability. Mark, you have it now.
Roger, S4B to orbit.
Downrange 479, altitude 96. Now approaching 65% of velocity needed for orbit. Velocity now 16,700 feet per second. Official time of liftoff 34 minutes 00 seconds .79.
Inboard.
Roger, inboard.
Flight.
Downrange 660 miles, altitude 95 miles. 78% velocity required for orbit.
15 Houston, go ahead. 15 Houston. Go ahead. Say again, 15.
Houston 15, we didn't call. You got something?
You've had PU shift and the thrust looks good.
Okay.
You've had level sense arm now?
Roger.
About 6 seconds to staging.
Stand by for mode 4 capability. Mark, you have mode 4 now.
Roger, in a good stage.
Roger.
Booster reports thrust okay on the S4B stage.
You have good thrust on the S4B.
Roger.
.960 miles downrange, 94.7 altitude, velocity 23,230.
Houston, everything's looking perfect. Predicted cutoff time 11 plus 37. Over.
Roger, 11 plus 37.
miles downrange, 93.4 altitude, 97% velocity, 98% of velocity required, 25,143 feet per second.
Okay, cut off, 11 plus 34.
Roger.
Booster confirms the S4B has shut down.
Okay, Houston, gamma motors are off, and the S4B oxidizer is 40, and the fuel is about 31.
Roger, 40 and 31.
Okay, Gordo, we got ourselves in a 93.7 by 88.9. Shut down on a VI of plus 25595. H dot plus 00008. Altitude plus 00932.
Roger, out, copy. Houston, IU shows you in a 92.5 by 91.5. Radar confirms that, and the booster is safe.
Okay, Gordo, good job. That was a very smooth ride all the way.
Roger. Houston, the booster is configured for orbit, over.
Roger.
Houston, have your Z-torquing angle.
Okay, go ahead.
Minus decimal 1 degrees, 1/10 of a degree, minus.
All right, minus 0.1.
That's correct.
had loss of signal through Bermuda. About a minute out of Canary Islands. To recap a moment, the measured orbital. Here's a call now to the crew.
Houston 15.
Roger, you're loud and clear.
Okay, the S4B tank pressure is about 41 on the oxidizer and about 21 on the fuel.
Roger, 41 and 21.
Apollo 15 in a 92.5 by 91.5 nautical mile Earth orbit, 1 mile out of perfectly circular. Communications through the Canary Island tracking station for about 4 minutes and 11 seconds total pass time. Coming up on loss of signal through Canaries.
Houston, about 35 seconds to LOS, and we have nothing further for you. We'll see you at Carnarvon as shown in the checklist at 5-2. Over.
Okay, Carnarvon at 5-2.
Flight Dynamics Officer reports that the data coming from the Canary Islands tracking station confirms the initial measurements of the Earth parking orbit. And we're expecting to acquire Apollo 15 again over the Carnarvon, Australia tracking station at 52 minutes ground elapsed time, about 30 minutes from now. And at 22 minutes 13 seconds ground elapsed time, this is Apollo control. This is Apollo control. 50 minutes, 34 seconds ground elapsed time on the mission of Apollo 15. Now approaching the Carnarvon, Australia tracking station. We're about a 6.5 minute pass over that station. Halfway through the first Earth parking orbit. Next time they pass over Carnarvon or over Australian subcontinent, the crew of Apollo 15 will be preparing for the Translunar injection maneuver, in which the spacecraft in S4B stage will break out of Earth parking orbit and begin the 3-day journey to the moon. Actually, the targeting will be toward where the moon will be 3 days from now. Still about 30 seconds away from predicted time of acquisition by the antenna at Carnarvon. We've had acquisition of signal. Let's stand by.
Apollo 15, Houston, through Carnarvon. Over.
All right, Houston 15, you're loud and clear.
You're loud and clear also.
Okay, the insertion checks are coming along very nicely. We're down through 21 of the checklist. And the cameras are out, and Al's completed his alignment.
Roger.
Hey, I only got one comment Jim's got for you.
Go ahead.
Houston 15. On the H2 purge, fuel cell 2, I cannot confirm since I have no readout of a flow indication or a caution and warning associated with that flow.
Roger.
And if you'd like, I could do it any time, and perhaps you could confirm it.
Houston 15. This is Houston. We're unable to help you on confirming that purge down here, Jim.
Okay, understand.
Go to SA. I've got some numbers on the P-52 for you.
Okay, ready, copy.
Okay, use stars 33 and 41. Down 05 was plus 00001, and the torquing angles were minus 00019, plus 00021, minus 00061, and they were torqued out at 50 minutes.
Roger, copied. On the torquing angles, a minus 3 zeros 19er, a plus 3 zeros 21, and a minus 3 zeros 61. Over.
That's affirm.
Thank you.
This is Apollo Control. Cabin pressure aboard Apollo 15 holding at 5.7 pounds per square inch. Heart rates for Scott, Worden, and Irwin respectively are 70, 83, and 88.
Houston, one other comment. Apparently sometime during launch, the RCS-B secondary propellant isolation valve closed, and we recycled it, got a great talk back.
Roger, Dave. Apollo 15 Houston, about 15 seconds to LOS, estimating United States at 1:30 GET.
Roger, 130.
And we've had loss of signal through the Carnarvon, Australia tracking station. We're standing by now for the post-launch press conference at Press Site 39 at Kennedy Space Center. And at 59 hours, 22 minutes ground elapsed time, this is Apollo Control. This is Apollo Control. We join the conversation in progress with Apollo 15 through Goldstone.
Through 27 on the checklist. The docking probe is out. Looks good. And standing by for a sequence arm and a logic check when you're ready.
Roger, we can do that now. Go ahead.
Okay, logic 1 on now, logic 2 on now.
Logics are good, you go for power on.
Okay, and we had one other little one. At about an hour, we noticed that the primary and secondary propellant isolation valves on quad delta were barber pole. We cycled the switch, and they're now gray, and the RCS check's okay.
Roger. I have a TLI plus 90 and liftoff plus 8 aboard pads when you're ready.
Can you stand by one, please, Gordon?
Okay.
Getting a little UV here. Okay, Gordo, I'm ready for the TLI pad.
Okay, this is the TLI plus 90 aboard pad, Jim.
Okay.
TLI plus 90, SPS/GNN. Noun 47 is 66938. Minus 052. Plus 190. GT for ignition is 004. 19er. 5699. Noun 81 minus 04254 plus 401 plus 49217. Attitude 180 166 002. HA is NA. HP plus 00210. 49401. 634. 49208. Sextant star is 40. 07905. 359er. Boresight star NA. Noun 61 plus 1604 minus 0, 3, 0, 0, 0. 1, 0, 9er, 9er, 0. 3, 4, 4, 9er, 2. GET for 05G. 0, 1, 7. 4, 3. 5, 8. GDC aligned stars are Deneb and Vega. 1, 1, 2. 1, 2, 8. 3, 5, 6. No LH. Go ahead. 15, Houston. Apollo 15, Houston, over. Apollo 15, Houston, we're not reading you. Over.
Okay, Houston, there's a breakup in a VHF, and Jim lost some of the first part of the transmission. Could you go through it again?
Okay, just what do you need?
Yeah, 947 through roll, pitch, and yaw.
Okay, Jim, 947 is 6, 6, 9er, 3, 8. Minus 0, 5, 2. Plus 1, 9er, 0. 933, 0, 0, 4. 1, 9er. 5, 6, 9er, 9er. 981, minus 0, 4, 2, 5, 4. Plus 0, 0, 0, 0, 1. Minus 4, 9er, 2, 1, 7. Correction on Delta VZ is a plus 4, 9er, 2, 1, 7. Roll, pitch, and yaw are 1, 8, 0, 1, 6, 6, 0, 0, 2. Go ahead.
Okay, read back for TLI plus 90, SPS GNN 66938 minus 052 plus 190 004 195699 minus 04254 plus 00001 plus 49217 180 166 002 NA plus 00210 49401 634 49208 40 0795 359 NA plus 1604 minus 03000 10990 34492 0174 Denham and Vega 112 128 356 and no LH.
Okay, Jim, your readback's correct. Liftoff plus 8 pad is 00800 6076 minus 175 02706. Go ahead.
Roger, 00800 6076 minus 175 and 02706.
Roger, and I have the TLI pad when you're ready for that one.
Go ahead, I'm ready on for the TLI pad.
Okay, time base 6 predict is 24023. Attitude for TLI 180 045 001. Burn time 555. 104011. 35599er. SEP attitude 359er. 077 320. Protection attitude 30 257 040. R2 align 0450 0380. Ordeal start 5645. Yaw 001. Ejection time 41600. Go ahead.
Roger, TLI read back. 24023 180 045 001 555 104 011 35599 359 077 320 301 257 040 0450 5645 001 and extraction at 41600.
Okay, a little static on two readbacks. Readback yaw for extraction and R2 align, please.
Roger, 040 and 0450.
Okay, readback's correct, Jim. 15 Houston, we have a question regarding the primary and secondary isolation valves. Over.
Go ahead.
We're wondering if you happened to just notice them, barber pole at 1 hour, or did you notice them close at 1 hour? Over.
No, we just noticed that they were closed at an hour. Apparently in the shuffle here, somebody probably bumped the one switch, which would do it.
Roger, you can't tie them to any other action or event there then, is that right?
Negative.
Okay, thank you.
Okay.
15 Houston, IU uptail to block. We have put in a second IU nav vector based on stateside data.
Tail to block.
15 Houston, we'd like poo and accept.
Poo and accept, you've got it.
15 Houston, IU uptail to block. You have a new state vector now.
Roger. CM uptail going to block.
Roger, my mistake. Also have a short update for your TLI checklist ordeal angles because of a slight performance difference in the S4B. Over.
Okay, go ahead, Gordo.
Okay, on the launch checklist page L2-30, bottom of the page, tell me when you have it.
Go ahead, Gordo.
At 56 minutes, flew FDAI number 1 to pitch equals 17 degrees rather than 16. And at the top of the next page, ensure FDAI number 1 pitch equal 14 degrees rather than 13. Over.
Roger, copied 17 degrees instead of 16. And 14 instead of the 13.
Okay, and then on the next page, 2-32, at 59:55, change 7 degrees to 8 degrees. Ensure FDAI number 1 pitch equal 8 degrees.
Copy 8 degrees.
One more on the cue card for TLI, down slightly below the middle. The long cue card that the CDR uses at 54 minutes. The 24 degrees should be changed to 25 degrees. Ordeal 300 lunar, 25 degrees.
Okay, we've got that, 25 degrees.
And then there'll be a 1 degree difference on the rest of the ordeal numbers.
Okay, looks like they all fit.
That's it. Apollo 15 Houston, we're about to LOS. Nothing further. We'll see you at Carnarvon at 2:25 GET.
Roger, 2:25.
This is Apollo Control. Apparently we have had loss of signal through the Vanguard tracking ship in mid-Atlantic. During that pass over the United States, the numbers for the upcoming Translunar injection maneuver were passed up to the crew. This maneuver slightly over an hour from now, planned at 2 hours 50 minutes ground elapsed time. The burn lasting 5 minutes 55 seconds with the S4B third stage. Place the spacecraft into trajectory toward the moon. Will increase the velocity by some 10,414 feet per second. Measurement of the Apollo 15 Earth orbit as it passed over the Texas tracking station. The displays here in mission control showed the present orbit at 96.5 by 93.8. During the launch phase, the heart rates of the crew of Apollo 15 were 110 for Scott, 104 for Worden, and 115 for Irwin. We'll be communicating with the crew of Apollo 15 through the Carnarvon station at ground elapsed time of 2 hours 24 minutes and some odd seconds, and almost continuous communications through Araya, or Apollo Range Instrumented Aircraft, between Carnarvon and Hawaii tracking station. The TLI burn begins just about the commencement of the pass over Hawaii, and at 1 hour 51 minutes ground elapsed time, this is Apollo Control. This is Apollo Control, 2 hours 24 minutes ground elapsed time. We've just had acquisition through the Carnarvon station, and Gordon Fullerton giving him a call at this time.
Bye-bye. Air 5-by also.
Okay. Houston 15, we're down to the middle of the TLI prep, and everything's in order.
Roger. 15, Houston.
Houston 15.
We're showing the manual attitude switches in rate and impulse, and we recommend rate command.
Roger, rate command. And the pyros are armed.
Roger.
Flight Director Jerry Griffin preparing to poll his flight controllers here in the mission control room for a go, no-go, which shows in the flight plan to be passed up through one of the aircraft in the mid-Pacific. However, it looks like the go, no-go signal will be voiced up to the crew just prior to the loss of signal here at Carnarvon. 22 minutes. Mark, 22 minutes to ignition for Translunar injection.
Apollo 15, Houston.
Houston 15.
You are go for TLI.
Roger, go for TLI. And the S4B oxidizer looks like about 36, and the fuel looks like about 19.
Roger.
We've had loss of signal at Carnarvon. However, we will leave the circuit up live for the relays through the aircraft in mid-Pacific, relay through the Guam station, for any continuing conversation with the crew of Apollo 15. 17 minutes 35 seconds to ignition for Translunar injection. The S4B with the Apollo 15 spacecraft now weigh around 103,000 pounds, or as you were, 309,630 pounds. After the burn is complete, the spacecraft will have shrunk to 103,000 pounds approximately. After Translunar injection burn, velocity will rise from the present 25,620 feet per second to 35,655 feet per second, an increase of slightly over 10,000 feet per second. About 20 minutes after burn cutoff, the S4B will maneuver to the separation attitude, and at 3 hours 20 minutes ground elapsed time, the Apollo 15 spacecraft will separate and do a turnaround maneuver and prepare to dock with the lunar module, which is housed in the spacecraft limb adapter atop the S4B stage. The 4 panels will shed away. The spacecraft, after docking with the lunar module, is ejected from the S4B stage. The lunar module landing gear struts are attached at the knee joints to fittings inside the spacecraft lunar module, or SLA as it's called in acronym. Springs eject the spacecraft at slightly over 1 foot per second. We're still about 2 minutes away from acquisition by the first of 2 Orion aircraft, or Apollo Range Instrumented Aircraft. From then on, we should have fairly continuous coverage until Hawaii, and the translunar injection burn, which is now some 14 minutes 6 seconds away from this point, will begin just at the start of the Hawaii pass, and from then on until going behind the moon, some 3 days from now, we'll have continuous coverage, continuous contact with Apollo 15. We've had acquisition of signal with the first Orion aircraft. During the separation and docking maneuver, we should have a live color television picture from the command module Westinghouse television camera.